Hello students, welcome to 17th lecture of chemical bonding and molecular structure. So we are meeting after a long time. So if you don't remember the previous points, just let us recap quickly. So previously we discussed about energy level diagram of molecular orbitals. And these are the orbital diagram. On left and right side we have atomic orbitals, and at the center we have molecular orbitals. Number of atomic and molecular orbital will be same. Energy of antibonding molecular orbital will be higher than the bonding molecular orbital, and total energy of molecular orbitals and atomic orbitals will be same. And how these type of bonding and anti-bonding orbitals will form, we discussed about those points. Then we discussed about the energy filling order in the orbital for F2 and O2 and for other elements up to 10 atomic number. Then we discussed about electronic configurations and molecular behaviors, in which stability of molecules was the first point, and according to this point, number of electrons in bonding molecular orbitals should be greater than number of electrons in anti-bonding molecular orbitals. If it is, then molecules will be stable, and if opposite is true or number of electrons in them are equal, then molecules will be unstable. Then we have bonding orders, that means difference of electrons in bonding and anti-bonding orbitals divided by 2, which represents number of bonds. If you find difference of bonding and anti-bonding orbital is equal to 2, then it represents single bond. If we have 4 electrons, then it will be double bond, and if we have 6 electrons, then it will be triple bond. So nature of bond will be 1, 2 or 3 depending on this number of electrons. Then we have bond lengths, and same thing will be applicable. Increasing bond length will decrease the bond strength, and decreasing bond length will increase the bond strength. That means they are inversely proportional. And lastly, we discussed about magnetic nature. For magnetic nature, we need single electrons. If our molecule contains at least one single electron, then it will be magnetically active, or it is called paramagnetic. And if all of them are paired up, all of the electrons in atom or molecule are paired up, then it will be diamagnetic, which feels repulsion from external magnetic field. Now in this lecture we will discuss about bonding in some homonuclear diatomic molecules, that means molecule containing two atoms of the same type, that means either hydrogen or chlorine or nitrogen, etc. So let us start with the most simplest molecule, which is hydrogen molecule, H2. We already discussed about its diagram earlier, but let us discuss it step by step in this point. So basics are mentioned, and we know that it is formed by two hydrogen atom, and both of them contains one electron in their 1s orbital. So these 1s orbitals of each hydrogen will combine, and it will form two molecular orbitals. One will be bonding molecular orbital, second one will be anti-bonding molecular orbital. Now both of these orbitals are s orbitals, and as we know, s orbitals always forms sigma bond. So both of them will be sigma orbitals. One will be sigma and second one will be sigma star. So configuration of H2 will be as mentioned here, sigma 1s2. Now note here, we also have anti-bonding molecular orbitals sigma star 1s, but it contains 0 electrons, so you do not need to represent it with electronic configuration of hydrogen. We only need those orbitals which contains electron. Remaining orbitals will be ignored. So our anti-bonding molecular orbital do not contain any electron, so that's why no need to represent it, although it will be present. Now let us try to find the bond order of the molecule. So as we know, we will have two different orbitals. One will be sigma 1s and second one will be sigma star 1s. As we can see, our sigma 1s orbital contains 2 electron and sigma star will contain 0 electron. So number of electrons in bonding molecular orbital, that means Nb, it is equal to 2, and number of electrons in anti-bonding orbital will be 0. So Na is equal to 0, so 2 minus 0 divided by 2, which is equal to 1. So this represents between two hydrogen atom there is a single bond. So it is mentioned here. And this means that two hydrogen atoms are bonded together by single bond. The bond dissociation energy of hydrogen molecule has been found to be 438 kilojoules per mole. That means if you have 1 moles of hydrogen gas, then you need 438 kilojoules of energy to split those molecules. Bond length is 74 and no unpaired electrons are present. That means this molecule will be diamagnetic. It will feel repulsion in external magnetic field. You can draw a diagram of hydrogen like this. It is the same as we discussed. Next one is helium molecule He2. Now maybe you will find this is not a familiar example because these type of molecules actually do not exist. Now let us try to find why these type of molecules do not exist. So as we know, we have two different helium atoms and both of them contains 1s2 electronic configuration. So it contains 2 electrons in one s orbital. So this 1s orbital of first and 1s orbital of second helium, both of them will form two molecular orbitals. First will be lower in energy and it will be bonding orbital, and second one will be anti-bonding molecular orbital. Now both of them are just like hydrogen and molecular orbital because we are mixing 1s orbital of each atom, so it will be the same. So you will get two different atomic or molecular orbitals. And diagram wise we can draw it like this. Suppose here we have 1s orbital of first helium and here we have 1s orbital of second helium, and both of them contains 2 electrons like this. So when they form molecular orbital, they will form two different molecular orbitals like this. One will be lower in energy than the atomic orbital and one will be higher in energy than the atomic orbital. So lower energy orbital is bonding orbital and higher energy orbital is anti-bonding molecular orbital. Now total number of electrons we have 4, 2 from first and 2 from second atom. So first 2 electrons will enter in bonding molecular orbital, but still we have 2 more extra electrons, so it must enter in anti-bonding molecular orbital. So in NB, that means number of electron in bonding orbital, we have 2, and as a Na, that means number of electron in anti-bonding orbital, we have also 2. So 2 electrons in bonding and 2 electrons in anti-bonding orbital. So as per our equation, bond order for helium is half of the number of electrons in bonding minus number of electrons in anti-bonding orbital, which is 2 minus 2, it will be 0. So 0 bond order is possible for He2. That means no bond are possible between two helium atoms. That's why He2 molecule is unstable and does not exist. Okay, so we can prove that using this theory. And similarly, we can also show that Be2 molecule does not exist, because if we draw the molecular orbital diagram or sequence for Be2 molecule, then you will notice number of electrons in bonding and anti-bonding orbitals are same. That's why bond order or bond number for Be2 molecule will be 0, just like helium. That's why Be2 molecule is not possible. Now let's move towards the next example, lithium molecule. So in lithium we have total 3 electrons. Electronic configuration of lithium atom will be 1s2, 2s1. So we have 2 orbital in one lithium and 2 in other lithium atom. So total number of orbitals will be 4. So 4 atomic orbital, that means 4 molecular orbital. Now out of 4, 2 will be bonding and 2 will be anti-bonding molecular orbital. So we have to find the number of electrons in each to find the bond order for lithium. So let us try to find it. So let us discuss step-by-step process to draw diagram for lithium. So we have to give the area for molecular orbital at the center, and at the side we have atomic orbitals of 2 different lithium atom, one here and one here. So as we know, helium will start from 1s. So 1s orbital, that means it contains 2 electrons for each. Okay, so these type of electronic configuration will be there. So these two orbital will form one lower energy orbit, that means bonding, and one higher energy orbital, that means anti-bonding orbital. So this is sigma 1s and this will be sigma star 1s. Then we have 2s orbital of both of them. So it contains only one electron, because in lithium we have only 3 electrons. So electronic configuration is 1s2 2s1. So these two again will form one bonding and one anti-bonding molecular orbital. So bonding molecular orbital is sigma 2s and anti-bonding is sigma star 2s. Now total number of electron 3 from first atom, 3 from second atom. So we have to arrange 6 electrons in this molecular orbital. So 2 electrons will fill in sigma 1s, 2 will be added in sigma star 1s, and then 2 in sigma 2s. Now 6 electrons are fully filled, so this last orbital will remain empty. So how many number of bonding electrons we have? So 2 here and 2 here, we have total 4 bonding electrons. And how many anti-bonding electrons we have? We have 2. So Na is equal to 2 and B is equal to 4. And in simple manner, electronic configuration will be sigma 1s2, sigma star 1s2 and sigma 2s2, and sigma star 2s will be empty. So this will be configuration for Li2 molecules, sigma 1s2, sigma star 1s2, sigma 2s2, and last one, that means sigma star 2s2 will be empty, so no need to mention it with our electronic configuration. So number of electron in bonding orbital is 2 plus 2, that means Nb is equal to 4, and in anti-bonding orbital Na we have 2. So difference is 2 divided by 2, that means 1. So lithium contains one single bond between them. So lithium 2 molecule contains single bond and it do not have any unpaired electron, as we observed in its electronic configuration and diagram. That's why nature of this molecule will be diamagnetic and it is present in vapor phase. Next one is carbon, and as we know, carbon contains total 6 electrons and the electronic configuration is 1s2 2s2 2p2 for one carbon atom. So carbon contains 2p orbital in atomic state, that means all of the 2p orbital will be there. We have total 3 p orbitals, px, py and pz. So if one of them is present, then remaining 2 will be there, but if it do not contains electron, then no need to mention it during the electronic configuration. Now let's find out its electronic diagram or molecular orbital diagram. So as we know, we have to divide it into different parts. On each side of these lines we have atomic orbitals of carbon atoms, and at the center we have molecular orbital. Now let us arrange the orbitals of carbon. So first will be 1s, and as we know, 1s will form two different orbitals, bonding and anti-bonding, like this. Now second one we have 2s orbital, and again you will get two different orbitals from the 2s, like this. One will be bonding, second one will be anti-bonding. And now we have 2p orbital. Now this will be new, and we know that we have three different orbitals in 2p, px, py and pz. And as we know, first will be z, which forms sigma bond, but if energy of pi bond is mentioned lower, then electron will be entered in lower energy orbital first. So as you can see in the arrangement mentioned in B2 to N2, orbital pi orbitals are mentioned as lower energy orbital. So splitting of p orbital will be something like this. First of all, two pi orbitals will be present here as a lower energy orbital. That means these two orbitals represents x and y, because x and y forms pi bonds, so they have lower energy. Next will be 2p Z. That means sigma bond formation from 2pz. It will be slightly lower than this orbital. Okay, so consider it as lower like this. Okay, this orbital represents sigma 2pz. Then energy of next we have sigma star, pi star orbitals, that means antibonding orbital, and then highest energy will be observed from this will be last orbital sigma star 2pz. Okay, these are pi star 2p x and y. This one will be sigma 2pz. This orbital is pi 2p x and y. Okay, so all the pi and sigmas are bonding and star orbital represents antibonding, and these two are, as mentioned earlier, one will be sigma antibonding, one will be sigma bonding. This will be sigma antibonding, this will be sigma bonding, just like before. Now total number of electrons, we have 6 electrons from each carbon. So 2 electrons in this first orbital, then next 2 in this antibonding orbital, then 2 electron in bonding orbital, 2 in antibonding orbital. Now up to this point, that means up to 2s, we already used 8 electrons, and total we have 12 electrons to arrange, 6 from each carbon. So remaining number of electrons, it will be 4. So first of all, these orbitals are present on same energy level, so both of them will get 1 electron, and if you have extra electron, then we have to pair up them. So pairing will be done here. So up to this orbital, all of the electrons are consumed, so remaining these orbitals are empty, and they are empty, so no need to mention them during the electronic configuration. So this will be electronic configuration of C2 molecule. It will start from sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. Then this completes the electronic configuration of C2 molecule. Now remaining atomic orbitals will be there, but with 0 electrons, so no need to mention it during the electronic configuration, but still we draw it. So if you count the total number of electrons, then you will notice we have total 12 electrons up to pi 2py2. So all of the electrons are already covered up to this point. So remaining orbitals do not have any electron. Now let us count the total number of bonding electrons. So let us circle them so that we can identify. So this is bonding, this one is second bonding orbital, and these two are other two bonding orbitals. So we have 4 bonding orbitals, that means number of electrons in them will be 8, because they are already, all of them are fully filled. Now number of anti-bonding electron, so we have 1 and 2. We have 2 anti-bonding electrons with electron, and it contains total 4 electrons. So difference is equal to 4 divided by 2, that means 2. So carbon-carbon contains double bond between them. So C2 molecule should be like this. It should contain double bond. So same thing is mentioned here, and here Kk is mentioned, and some of the portion of electronic configuration is by mistake not printed here. So we already discussed that separately, that's why. And Kk represents these two orbitals. First orbitals are referred as K, capital K shell. Now if you notice, none of the electrons were unpaired in the electronic configuration of C2. That's why it will be diamagnetic. And these diamagnetic C2 molecules can be detected in vapor phase. Now it is also important to note, double bond in C2 consists of both pi bonds because of the presence of 4 electrons in 2 pi molecular orbitals. That means remaining orbitals, sigma orbitals, also contains electron, but each of them will be cancelled out with antibonding sigma orbital. That means if electrons are present in sigma 1s, then electrons are also present in sigma 1s, sigma star 1s. Similarly, if electrons are present in sigma 2s, then electrons are also present in sigma star 2s. So they will cancel out each other. and number of electrons are present in pi bonding orbitals only. That's why both of the bond in C2 molecule are considered as pi bonds. Actually it is not true, but according to MO theory they are pi bonds. And generally if you have double bond, then first bond will be sigma and second bond will be pi. And in actual term it is true, both of them cannot be pi bonds. In a similar fashion, the bonding in N2 molecule can be discussed. So let's talk about O2. So this will be the electronic arrangement for a O2 diagram. On both sides, as usual, we have atomic orbital here and atomic orbital here, and at the center we have molecular orbital of O2 molecule. Now as we know, number of electrons in each oxygen atom is equal to 8. So 8 plus 8, we have 16 electrons to arrange. So increasing order of orbitals are mentioned, and as we know, for O2 and F2 order will be flipped. It will be flipped slightly. So order were already discussed in previous lecture, so you can go and check what is the order for O2, and it is also mentioned here. So 1s orbital will be present at the bottom, but we didn't represent it to reduce the confusion. So we started from 2s orbital. So keep in mind 4 electrons are already arranged in sigma 1s and sigma star 1s. So 4 electrons are already consumed. So remaining electrons will be arranged from 2s orbital. So here we have 2s sigma orbital. So 2 electrons will be added here. Then next 2 electrons will be added in sigma star 2s. Then next 2 electrons will enter in p orbital, in pz orbital, which is sigma 2pz. Then in next 2 orbital, that means in next pi orbital px and py, first 1 electron will be arranged like this. Now let us count the total number of electrons. So keep in mind already 4 electrons are already added in sigma 1s and sigma star 1s. So later we arranged total 8 electrons. So total 12 are complete. So next electron will be added in these two orbitals, then they will pair up. And again we have similar energy containing two antibonding pi orbitals px and py. So each of them will get 1 electron. So as you can see, total 16 electrons are complete. And something different is observed here. It is 2 single electrons. So in O2 molecular formation, you will get 2 single electrons. Now let us find total number of bonding electrons and anti-bonding electrons. So as a bonding electron, 2 electrons will be in 1s sigma orbital, then 2 electrons here, 2 here, and 4 here. So total we have 10 bonding electrons. And now let us count the total number of anti-bonding electrons. So in 1s sigma star orbital, we have 2 electrons, and later we have 2 electrons here and 2 electrons here. So total 4 electrons here and 2 in previous. So total 6 electrons in antibonding orbital, and total number of electrons are 16, which should be, so we have total difference of 4 electron divided by 2, which means double bond. So O2 molecule contains double bond, and we know that. And this molecule also contains single electron, so that means it should be paramagnetic, and practically we can verify it, which is mentioned in this case as well. So these are the electronic configuration of some molecules, and you have to find electronic configuration of remaining elements up to 10. Okay, try to find the remaining elements, as for example nitrogen, yourself, and if you find any difficulty, feel free to ask. We will discuss it in detail, and in next page this diagram is also mentioned for your help if you require. Some of the molecules are mentioned here which we already discussed, and some of them which we didn't discuss. So you can use the help and try to find the diagram and electronic configuration of remaining molecules, and try to find the number of bonds in them. Okay, especially try to find number of bond or bond order for nitrogen, and if you find any difficulty, feel free to ask. We will discuss it in next lecture. Thank you.